For our next talk in this segment, we have Nikesh Garera. Nikesh comes with a deep background in natural language processing, spanning 18 years of industry and research experience, along with 35 patents and publications. He did a master's from Carnegie Mellon and a PhD from Johns Hopkins, and has worked at AI tech companies in US and India, such as Cosmix and Walmart Labs. At Flipkart, Nikesh leads our data science efforts for machine translation, NLP, and conversational AI technologies. He'll be speaking to us about various challenges encountered in building translation models for Indian languages. He will also cover some of the practical considerations in scaling up and productionizing these models. Can we please have Nikesh on the screen?
Hi all, thank you Sarika. I hope you all can hear me and see my okay. All right, hi all, thank you Sarika, and I hope you all can hear me and see the slides. Yep, okay, thank you. All right, good afternoon folks. So I'll be talking about how we went about basically building various machine translation models at Flipkart, right? The entire journey, why we went about it, what areas we solve for, and so on, right? But the motivation, let's start with that, right? So essentially, yeah. So vernacular has been growing in India at a rapid pace over the last, if you see on the graph on the right, over the last many years, right? A number of Indian language and internet users have been growing exponentially. The problem is a lot of the content is still in English, and there is an inability to comprehend that. And because you cannot comprehend it very easily, there is a lack of trust, lack of confidence, which results in lower engagement, people not sure about buying things, and all of that, right? So how can we solve for that? We basically provide the content in user's own language, right, to build a familiarity and the trust, which has shown now that helps in increase engagement, conversion, and so on, right? So let's look at the various kind of pages, right? Solve for, right? So let's look at. Here you see an example of, for example, on the extreme right, reviews being translated and shown in Hindi, search working, right? Search results are being shown in Hindi, and with all of these, we are already now live in 11 Indian languages. That was basically what our mission was. How do we provide all of Flipkart content, whether it's product catalog, whether it's reviews, whether it's question answers, whether it is search, addresses, and so on, right? And then you can see the various areas in over here, right? So there is catalog data, there is product descriptions. So catalog attributes are mostly the key value attributes. They need to be transliterated. I'll talk more about that. But there is long form content like product descriptions, user reviews, which need to be translated. Search queries, which end up actually being multiple languages. That they could be there, what we call code mixing, right? Two languages mixed in the query, Hindi English mixed together, addresses, customer service chats, and so on, right? Doing this manually, of course, is not scalable, right? So, and then of course, the one choice would be that why don't we just try off the shelf machine translation model? But there are various challenges with that. Uh, in this talk, I'll focus more on the areas of product description, user reviews, and search queries, and go a bit more deeper into that. Uh, so the challenges, right? When we train a machine translation model, the first challenge is how do we get training data? Any data science model needs training data. In case of machine translation, what we need is something called a parallel corpora, which is basically parallel, it means basically the same sentence. Let's say English, we want to translate to Hindi, the English sentence translated in Hindi, and millions of such pairs, right? The There are various open domain data sets available, but a lot of them are not for Indian languages. There is a lot of data available in European languages such as Europal, Paracrawl, and so on. There are now efforts in India as well, right, using Indic NLP and all of that. It is still not, I mean, it's still lower in volume. And not only that, while these are open domain data sets available, what we also need is basically in domain data, right? E commerce data, right? Which may not be as clean, and you can see the kind of like noise, right? Over here, there is improper sentence structure. There may not be they may not be grammatical. There would be spelling mistakes, punctuations are missing, pronouns and articles are getting dropped, there are emojis being added, characters repeating, and so on, right? And oftentimes language is getting mixed, right? For example, nice product, gajab camera quality. Dhasu product. Dhasu is more colloquial, depending on the region and so on, right? Abbreviations like awesome, OSM product and so on, right? So any model trained on the open domain data will not work well, not only because of the vocabulary limitations, but also because of the this noise, right? So now let's look at some examples, right? When we actually tried the state of the art open domain translation models, right? Something as simple as a good quality product for you, right? On the right, you see the result of the state of the art model. ऑफ द शेल्फ मॉडल आपके आपके लिए एक अच्छी गुणवत्ता का उत्पाद. Now गुणवत्ता means quality, utpad means product. It's a correct translation, but if we show this to our users, it's very difficult for them to understand. People in India would understand quality as quality, product as product. Something like, for example, our boots are available in eye-catching looks, right? Now, eye-catching looks, again, people understand it. You really don't need to translate, and if you try translating it, it actually becomes very funny. Aankh ko pakadne wala ro, right? Something like ultraviolet ray, people would understand. You really don't need to do the pure Hindi translation. I can't even pronounce it. I'm sorry. So I think, and then if you look at some more interesting examples like you maniacs, maniacs, Aap Pagal, and movie names like Planet of the Apes, right? I mean, that's just a movie name. It needs to be translated. It means the same English was written in Hindi script. You don't have to translate it, right? And it's difficult to figure out that this is actually a movie name and doesn't need to be translated and so on, right? You need that additional knowledge for it. So, how did we go about solving for these challenges, right? So we train. I'll basically first describe our overall system, right? So we still, I mean, have a pre-training step. So the pre-training is done on all the open domain data that we can get. It's still valuable. As much as open domain data we could get our hands on, we would train the initial transformer model, which is the standard approach now used in translation literature. And then we'll further then fine tune it on the in-domain data, not only the small amount of manual tag data we have, but actually generate a lot of in-domain data in a noisy manner, in a synthetic manner, and so on. And then further separately do a transfer learning step for modeling colloquial translations. I'll give some more examples of these as we go over the journey of building these models, right? And then retrain the model based on this data generated. So let's look at how did we solve for the first problem of, okay, we have a pre-trained model, but it really needs to work on e-commerce in domain, and how do we generate that in domain data, right? So okay, this is just a summary of the quick slide on the transformer-based approach. Basically, we I mean, yeah, we can you can look at the reference more in details. It's generally state of the art model. There were some challenges we faced, which I've shown on the right. For example, when you try a transformer-based approach in for the very long form sentences like product description, which has like many sentences, it doesn't work very well. We have to tokenize it, work at a subword level, and so on, right? But anyway, I think we'll talk more about these are generally approaches available in literature. You can read up more on it, right? But I'll talk about what is not there, right, in the literature, and how did we basically solve for that, right? And for example, solving for lack of data. If you don't have data, then how do you train such a transformer model, right? So we know that there is a lot of monolingual data available. Monolingual means data available only in one language. For example, English. We have a lot of English product descriptions, English reviews, English search queries, all of that, right? We may have limited data in Hindi as well, because people may type in Hindi in reviews and so on, but definitely not compared. I mean, much lower in volume. So we start with the initial parallel corpus, which is manually tagged, and then we generate using that. We generate take all the monolingual corpus in English. We do a forward translation, and similarly we do a backward translation from Hindi to English. And these are basically our synthetic corpus, right? These are translations. Some of them are good, some of them are bad. We cannot directly add them to our training data. So we have a very key step over here, which models what is the quality of translation, right? and that's an interesting step as well. I'll try to explain a bit more on that. And if it is good quality, then we add it back to our translation corpus, and we basically increase the amount of data we have. If it's poor quality, that's valuable as well. We know this is where the model is going wrong, so we need labels for that. So we send it to Oracle, which is the manual tagging team, uh, and they correct the translations, and that's fed back in a bit of like an active learning framework in the manual tag data, and then we retrain the model and so on, right? So this way we were able to solve a lot of the lack of data challenges. I will and there were some more steps. I will talk a bit more about that, but let's look at, for example, how do we while we may get reasonable translations, but we still will not get colloquial translations using this, right? And for example, when we in this slide you see how we solve for colloquial language challenge, right? You can see that for every translation, for example, buy this keychain from confident क्योंकि ये kitchen confidence से है, kitchen confidence से है, gets a poor probability. And something like a good translation, package includes package में शामिल 0.94 gets a high probability, right? And you can see that these are, I mean, so the way we estimate the probabilities using a bird-based model, which is trained on open domain data. And the problem with that is that non-colloquial translations are also still scored very high. Uh, so how do we then model colloquialness, right? So we trained a separate language model, a transformer language model, which was trained only on Flipkart e-commerce data such as reviews, and it would try to predict whether this sentence is colloquial or not. For example, we would take various candidates from the translation model, such as "यह उत्पाद अच्छा है," "ये उत्पाद अच्छा है," "ये product अच्छा है," and you would see that the so on the left numbers which you see 28.8 and so on, those are language model perplexities, which basically tell how probable the sentence is. But in the perplexity, lower the better, right? So you see that here product acha hai gets the lowest perplexity when re-ranked using this separate transformer language model, right, trained on Flipkart data. Similarly, you see that something like tempered the glass. Actually, the colloquial sentence is tempered the glass visibility का त्याग किए बिना आपके डिवाइस स्क्रीन पर स्क्रैच से बच पाएगा. So visibility is colloquial. Everybody understands that scratch is colloquial. You don't need to try to translate visibility or try to translate scratch as kharoch or something. So another challenge is once you re-rank it using the language model, different sentences, right, will get different perplexity scores depending on the length of the sentence. So you can't simply just put a threshold on the perplexity and take the ones which are cross a threshold. You need to figure out how to model them in a relative sense, and that was another step that I won't have time to go into detail of that, but that's another step to then finally tell, okay, be able to re-rank using colloquial model, right? So now let's look at how did we do, right, with respect to I mean, of course, these steps make intuitive sense, but how well, when we look at the numbers, does it actually provide at scale better translations? So you see here in this table a comparison of the Flipkart model, which uses the various steps I talked about, data augmentation, modeling for colloquialness, and all of that, compared to state-of-the-art external model, right? What these numbers are blue scores. So blue is a standard evaluation metric used in machine translation literature. It basically determines the overlap, right? Some kind of n-gram overlap between the candidate translation and the reference translation. So the higher the overlap, the higher the blue score number. And you see that the FK model gives significant improvements in blue scores. The challenge with blue score is that it may not give always a fully correct picture because some of the semantically similar translations, right? Maybe a different word was used, but it had the same meaning. Maybe it was a more colloquial word or whatever, right? May also get dinged. So we have, while we see improvements here, we also did a separate evaluation, which is basically asking a subject, which is a bit more subjective evaluation, and users could say basically that, okay, is this, I mean, the ops team, the tagging team could say whether this translation is good, it can be better, bad. Bad means it's really embarrassing, it doesn't convey the meaning at all. If you show it to our users, it will look really bad, right? Can be better, it's I can understand the meaning, but it can be more fluent, and good means it's really good, it's fluent, and so on, right? So you can see that with the Flipkart model, we have a bad error rate of really low bad error rate compared to the state-of-the-art models. The main challenge why we see a very high bad error rate in state-of-the-art models is because of they're not able to model for colloquialness as they are trained on open domain data. We see this we see these improvements in various languages: Tamil, Telugu, Bengali, and these were the initial results. The V1 model that we trained using these steps. There were multiple iterations done on these models, and now for various languages, we are able to basically let me just see if I can. Sorry, yeah, we are able to get improvements on. I'm sorry. We are able to get improvements, as you can see in this table. Compared to the initial V1 model, we have accuracy, resulting from 90 to even 98 plus percent, right, across various languages. Uh, we also apply these approaches on reviews, right? And you can see the blue scores on various lengths of reviews, short reviews, medium reviews, long reviews, and how the Flipkart model works better. And also similarly in the manual evaluation results of good, can be, better, and bad, right? So we looked at how how did we solve for some long form content such as product descriptions, reviews, which can be both medium length, long length, and so on, right? Uh, how did we model for colloquialness and so on, right? Now let's look at another interesting challenge, which was the third area which I was going to talk about, which was the search queries, right? So in search queries, the first problem, right, while is basically we were already seeing English queries in our English website, right? People were already searching in English. They were just using the English letters, the Roman script, right? There was a significant volume for this, and the search results would not look very relevant because a lot of the content, the catalog and content would not have these words, right? So we had to first, I mean, while you see here translations, right? You see a English query, Samsung phone 8000 wala, and the correct English translation, and you see some of the issues like misspelling, brand misspelling, spell errors, articulation gap, a free flowing text, and so on. But even if we even if we, before we attempt to translate this English query to English, we actually first detect whether this query is English or not, right? So we built a separate language detection model which would detect whether this query is English, which would detect at every token level whether this word is Hindi or English, and then depending on the number of words, whether this query dominantly English or dominantly Hindi, and all of that, right? So once we have determined that, that's when the translation steps come in, right? And that is where we will focus more on that. And I think so on the translation, we could approach it in two ways, right? We basically have already a translation model which translates from Devanagari, which is Phool Ka Gamla, to flower pot. We had trained such models before I showed you, right? So we could just apply a transliteration step, which takes the English query written using English letters, Roman script, and transliterates it to Devanagari, and then the translation basically comes, right? The problem with this is that we could have errors because in transliteration, the errors which are there in transliteration would get compounded into translation. There are various variations, like as you noticed in the previous slide, there are misspellings and all of that, which kind of really can compound in transliteration, and it's difficult to then model it in Devanagari compared to being able to model it in a Roman script. And we realized that we could model all those variations much better in Roman script. But what we needed was a larger training set to capture those query variations, right? In order to build a direct English to English translation model. So uh, that's what we ended up doing. We basically had a direct model, but there was a step required, which was data augmentation to capture query variations, right? And there were various steps that we took to generate the synthetic data. I will summarize them as follows. So we have been given label data, right? And we can basically use that to train an autoencoder model, which will basically try to reconstruct the label, right? We could add noise, such as we could mask the one of the words in the label input label, and try to then generate the correct label as a ground truth. Drop the characters, which could model things like spelling errors. Word order I mean, masking could model things like articulation gap. word order permutations. Sometimes, uh, people may not write in the correct order. They may not put correct grammatical phrases and so on, right? So, when we applied these steps to generate additional synthetic data, which basically became part of our training data, we were able to see blue score improvements through most of these steps, not necessarily all of these steps. And I'll show you those improvements here, right? So we tried various transformer models, bath based, T5 based, vertibird, and so on. In general, we tried comparing these as baselines, but once we added data augmentation steps, right? Like autoencoder, character drop, masking. Most of them gave improvements over here. And then finally, even with respect to overall our accuracy numbers, we saw that modeling for these variations and directly building a model results in significantly better accuracies, right? So you see, the live model was the old live model, which is basically um, uh, uh, the live model was an old model, which was transliteration plus translation, and we will be able to we show that if we just directly model English to English, right, we see a significant improvement in accuracies. Uh, Not only overall, but also in various distributions like head queries, torso queries, tail queries, right? So yeah, I'll take some questions. I see there are some questions. I'll take some questions at the end. And so now let's go to another challenge, right, that we faced basically with respect to solving for search. The problem with search is that you need a translation in real time, right? You, for something like product descriptions, reviews, you can do it in an offline manner. You can train large deep learning architectures, right? But for this, we needed to solve it in real time, and the large architectures really had high latencies, right? We solve that using a knowledge distillation based approaches where we train a large teacher model and then we use the predictions of that, either labels or the probabilities of the labels and so on, to train a student model, right? And then the student model is a smaller model, but if we do it in this manner, we are able to not compromise much on the quality but reduce the latency significantly. There are a couple of references given here, and I encourage the audience to look for more details into that. But let us see exactly what the impact of this was, right? Uh, so the large model, which is a teacher model, had 6 layers, had a reasonable blue score, but the latency was very high, up to 100 milliseconds, right? Then we tried various smaller student models. So Q is basically the quantized models, and layers, one layer, different loss, cross entropy loss, sense and channel loss, and so on. And we could see, reduction in latency significantly. And the final model, which is the model trained using the OpenMNT architecture as a student model, resulted in 14 milliseconds. If we actually don't perform knowledge distillation and we just train the OpenMNT model, right, we see a significant drop in blue scores, which is 38.5. But if we actually use that and train a student model using the prediction from teacher, we see that the blue score has dropped very, very slightly, but the latency has significantly improved from 200 milliseconds to 14 milliseconds, right? So that's another challenge that when we deployed. So ultimately, I mean, yeah. So we went live with this model. We were able to show good improvements in accuracy, and of course, it also resulted in significant gains in conversion, CTR, and so on. Right? All the models I talked about, product description, reviews, search queries, are all live across all Flipkart content. Right? Uh, so here are the learnings, right? Here are basically summary. Had the problem that, hey, translation looks like, initially when we started, looks like it's a solved problem. There are so many translation models out there, but when we applied it to the data that we had, that our users were giving, we realized a lot of challenges, a lot of noise and so on, right? And we also saw that basically, uh, if we just apply the off-the-shelf systems, the challenges which we saw, right, and the quality and all of that. Uh, so we basically overall essentially were able to leap forward from that initial model, right, of just using open domain data, but being able to make it work for our domain data using these steps, right? First step was challenge was we didn't have parallel data and domain data. We showed how we were able to generate forward backward translations add a quality step and feed it back, use transfer learning to fine tune it on that in domain data, the open domain models. Noisy data, generated synthetic noise, added noise in a synthetic manner, artificial manner, mod, added subword modeling to further model for the noise, trained a separate colloquial model which were able to filter colloquial translations, added a language detection model to detect code mix queries, and built a direct English to English model. And there is no today there's no parallel corpora available for English to English, right? Especially for e-commerce, right? So I think we were able to generate that with this data augmentation step and show the direct model works better, significantly better, and then solve for deployment considerations like latency for real-time translations using knowledge distillation, right? So that's basically the summary. I think I'm mostly done. Let me, thank the team. There's a lot of my colleagues have helped in these efforts across various functional data science, product ops, engineering. We also had academic collaboration with IIT Patna, and that really helped with solving for review translation, which was a very challenging task, and of course our leadership as well, right? Let me take some questions now. So I see a question about. Let me see. Does manual review done by reviewers is done by multiple people for the same input? Translation subjective even when manually done. The translation as well as scoring of translation could be messed up in models. Yeah, I think that's a great question. The something like a translation is a subjective problem, right? What is interesting is that from the point of view of conveying the meaning, right, it's not very subjective. So I think we were, hence you would see low good scores, but you see generally high can be better scores. People would align on can be better, but may not really align on. People will align generally on bad, right? What's bad, right? And we want to make sure that is the case. But yeah, so we have so far only we have not uh, done multi annotator translation and looking at agreements. We generally know that for bad, the disagreement is low. And as a first step, we want to avoid all bad translations. And then as we improve further from can be better to good, handling, measuring subjectivity, right, using multiple people would be very valuable. That's a good point. Yeah. Cool. I think, are there any other questions? Yeah. Thank you all for that's it. So then, thank you all for your time. I'll be at the networking area to discuss more. Thank you.